Right.
Yeah, it's not big and it's only.
If you answer every question on the bronze test with the word magic, you'll pass. Have you all got that picture?
Yeah.
Yeah. Okay.
Yeah.
Well, you've probably all seen that picture. Have you ever sat in your glider and looked out at the wings and thought, there's nothing holding me up? I mean, obviously Barney can't even see his wings. So yeah, this is the simple thing. If you fail to believe in the magic, the aeroplane will no longer fly.
Lucky.
Right. And of course, the first person to start deciphering the magic, obviously they've been to Hogwarts, was the Wright brothers. For Hogwarts, you can read date no higher. But the serious point is they were the first people to realize that an aircraft isn't like a ship. It operates in 3 axes. And that obviously part of it, apart from providing lift, is control. And we'll try and cover all of that in the next few minutes. Okay. Again, moving fairly quickly through this, I would think. When we're considering the aircraft movement, we know there are 3 axes, the vertical, longitudinal and lateral. Okay, the movement about the lateral axis we refer to as pitch, and we'll know that's controlled with the stick fore and aft. Notice that the movement is around the centre of gravity, and centre of gravity will come into what we're saying quite a lot later on. Movement around the longitudinal axis, running from the nose of the glider through to the tail, is roll. And moving quickly on, movement around the vertical axis we refer to as yaw. Okay, first lessons, we look at the control of the aircraft in pitch, roll and yaw. Everyone happy about that? Yep. Nods will do. Okay, go back again. Before we get too far into this, we're looking now at the airflow that produces lift. The convention is to show this as the air moving across the airfoil. This is only true if you're flying at 40 knots in a 40-knot wind. Most of the time, the aircraft's moving through the sky, but because this refers to wind tunnel work and because you can't follow a moving airfoil, the convention is to show the air is moving across the wing. We've all played with simple balsa chuck gliders. Basically, the wings are just a flat sheet. Do they work? Yes. If the wing is not inclined at all to the airflow, all they produce is drag, and a very small amount of drag, the air that's moving past. The actual cause of drag is simply that the air has to be accelerated out of the way and back in at the end. Any time you're putting energy into the air, it's got to come from somewhere, and basically it comes from the aircraft. Okay, and appears as drag holding it back. The air moving past the wing can be laminar or turbulent. The best way of thinking about laminar flow is a well-ordered motorway with traffic on the slow lane bumbling along at 50, in the centre lane they're bumbling along at 60 and maybe 70 in the outer lane. And all is peaceful, it all goes well, until the one who wants to go at 80 switches to the inside lane because it's empty and causes disruption. Okay, with cars changing lane frequently, getting in each other's way, everybody's slowing down, so the net speed is less. And turbulent flow is much the same as that. Okay, something can disrupt it. In the case of the motorway, it could be a car breaks down on the inside lane, which pushes traffic out, and you've got a mixture of air moving at different speeds, starts to eddy around and causes much more drag. All happy with that? Nod, yes. When air is moving past the surface, the air moving past the wing, the flow may be laminar, but is much more likely to become turbulent at some point. In fact, for most glider wings, the transition happens round about 55 to 60% of the way to the back. It can be delayed by changing the shape of the airfoil. It's relatively easy to keep the airflow laminar where it's moving across a smooth surface that's getting wider, thicker. As soon as the airfoil starts to narrow, the air is much less likely to follow it. And at some point, there'll be a transition. You might see on lots of gliders something to make that transition happen. There are in fact two sorts of turbulent flow. Some turbulent flow is quite small, fairly close to the surface, and that's generally referred to as attached turbulent flow. However, if the airflow breaks away completely from the surface and you've got slow moving air next to the wing mixing with air that's moving smoothly further out, then you get detached turbulent flow and much more drag. So on some gliders, you'll see a strip of zigzag tape or something similar on the underside, round about 2/3 of the way from the leading edge. And the idea in that is to trip the flow, make it turbulent, but keep it attached to the airfoil. Okay, that works. In fact, on one glider we were testing once, we actually tried that on the top surface, and it made the ailerons work because a very bad airfoil was causing the airflow to detach. Okay. So if we take our simple balsa manual glider and incline it to the wing, to the airflow, we describe that as an angle of attack. Okay, usually referred to as alpha. In a normal airflow, the air passing under that flat surface will be deflected fairly smoothly downwards, but the air flowing over the top can't follow the sudden change in direction, and it becomes turbulent and detaches. In this very simple airfoil, most of the lift is caused by the air being pushed downwards, the change in the direction. You're not getting much lift caused by the air flowing over the top. Okay, it's not a very efficient one, and the proportion of drag to lift is much worse than for a modern airfoil. Okay, what we get, of course, is a total reaction. The airflow past is pushing the airfoil in the direction shown, some of which is vertical, which we call lift, and some of which is horizontal. We don't want it as drag. Okay, if we improve the shape of the foil, in this case, the air flowing over the top can remain smooth, at least for most of the way back. And now we're getting lift from a second source. We'll explain that in a minute. There's a sort of controversy about how lift is produced. In fact, it's produced through both the methods, we'll see. And this one is producing much more lift for much less drag. And of course, that's why wings are the kind of shape that they are. The tendency now is to push the thickest part of the wing further back. It actually produces a bit less lift, but keeps the airflow attached, and the total lift to drag ratio is improved. Next thing is some series of videos of a wind tunnel using smoke stream, so you can actually see what's happening. Have some of you seen this? Okay, so you can see using a pulse smoke, the air actually flows over the top, and you see when they slow it down, do it in slow motion, the air moving across the top of the airfoil is moving more quickly. All those pulses were sent at the same moment, but the air at the top is actually moving fairly quickly. Now, where air flows more quickly, the pressure reduces, the molecules simply have less time to bang themselves against the surface, which is essentially what air pressure is. And you can see now what happens if you increase the angle of attack from almost zero. As you increase, the airflow is deflected more, but at some point, the angle is too great on the top surface, and the airflow starts to detach about there. And you can see the turbulence that's created. Remember, all that energy to make the air turbulent is coming from the aircraft. Most airfoils start to get detached airflow at about 15 degrees. Plain airfoils, that is. Very seldom will you get it to the kind of extreme angle shown there. So it's starting to detach. It says it attached, but it's not really attached there. And there it's completely stalled. The air moving under the airfoil is still okay. It's still moving. So there is some lift produced by that deflection. And notice as soon as the airfoil moves back in line, the airflow immediately reattaches. And the lesson from that, if you start to get a stall, immediately reducing the angle of attack, reattaches the airflow. All happy with that? Want to see it again? Or I think it's all fairly straightforward. The whole thing is really. Okay, so this picture is basically showing the stalled airfoil. The air over the top can't follow that contour. It becomes detached and very turbulent, which represents the high amount of drag and a much reduced amount of lift. Okay. And say that tends to happen around about 15 degrees. It's not the only source of drag. By the way, the drag we're referring to is nothing to do with strange clothing on men. Okay, there are forms of drag which are not really to do with producing lift. Tend to be referred to as parasitic drag. First one, form drag. The air simply has to move aside to let the aircraft through. The energy to push it to one side and bring it back together again is form drag. Second type, skin friction. If you've any problems, surface roughness or hinges sticking out or gaps not taped up, that sort of thing will cause skin friction. And there the air can't remain laminar. It would tend to get very turbulent and create drag caused by the friction across the skin. And then there's drag caused by the airflow over the junction between, for example, the wing and fuselage interfering with each other. And if we think about gliders, obviously very few gliders would be the shape of this one. Every time you've got a wing, you've got two interference areas where it joins the fuselage. So it's four. The same for the tail, but one reason why gliders have T-tails is it reduces the points where interference drag is created. Now, it's not the only reason, but it's one reason why T-tails produce less drag than conventional tails. All those forms we've just looked at are parasitic. They aren't strictly necessary. In fact, there have been attempts to reduce them. For instance, some of the early Polish gliders in the 1960s were very, very slim. The pilot was almost lying down and staring at the world from between the feet to get the fuselage cross-section as small as possible. The problem with that is the pilot needs to function as a pilot, and there are limits. But this sort of grad we're now looking at in the top left hand, we know that now there's high pressure beneath the wing, relatively high pressure, and relatively low pressure above the wing. The actual variation is a fraction of 1% because the total pressure on the wing is much higher. But air being a fairly fluid thing will then tend to want to flow from high pressure to low pressure. And we see that in two ways. The air moving across the top of the wing, seen on the top right, tends to move in towards the fuselage because the pressure is lower. The air underneath tends to flow outwards. That becomes very marked at the tips where there's nothing to prevent the air from below moving round above the tip, and you get the vortex. Okay, so wingtip vortex is one cause of induced drag. You can't create lift without some forms of induced drag. You can minimize it, but you can't create lift without it. The second sort is shown in the lower diagram. Overall, the airflow is deflected downwards by the passage of the aircraft, and it's a simple bit of Newton. If you push something down, you get an equal and opposite reaction pushing up. Okay, so we have those two forms of induced drag. Can't avoid them, they're there. This next clip shows, it's actually a wilga, sometimes used as tugs, flying through a smoke trail, which shows the induced drag very, very clearly.
Wingtip vortices are circular patterns of rotating air left behind a wing as it generates lift. Here we have me and my wilga. flying through a couple of smoke bombs we set up to do the vortices demonstration. We'll see it slow-mo here. Watch as it passes through. You'll see those vortices form very quickly behind the aircraft. Look at those things spinning. That air just wants to escape. Wingtip vortices can pose a hazard to aircraft, especially during the landing and takeoff phases of flight. The intensity or strength of the vortex is a function of aircraft size, speed, configuration, flap settings, angle of attack. So when you're taking off or landing, you want to kind of avoid those.
Right. You probably know that if a large, heavy aircraft 747 takes off, they then have to leave several miles of airspace behind to avoid the vortex before a light aircraft takes off. And in fact, at Lasham, they lost 2 K-13s when a heavy jet landed unexpectedly. One coming in behind the jet was rolled inverted and landed on another. The aircraft company paid for the replacement K-13. Surprisingly, the crew walked away, the glider crew. Obviously, we said the main vortex is the one from the wingtip. And one reason why gliders have long, narrow wings is to reduce the proportion of wingtip to span. This overall reduces the drag. You've probably seen winglets. Okay, the idea in the winglet is you don't need to have a big difference in pressure on either side, depending on the winglets. So the vortex from it can be very, very small. Right, that's probably seen as a good thing, reducing the drag. But as we'll see in the next bit, it's not all good news. Oh yeah, I've forgotten to put this one in. The obviously the cartoon is intended to teach geese that you could get other geese to tow you through the air. But geese do fly in V-shaped formations. Why? Anyone going to volunteer? They do it quite precisely, and quite often they fly over Seiford, going to and from Doxy Marshes. No volunteers? Think about the wingtip vortex. Okay, the vortex on the outside of the wingtip is moving up and a little bit forward, moving down. If one goose is flying behind another, it's using the vortex off the wingtip to actually give it effectively some lift. The goose at the front doesn't get any benefit, but it doesn't actually lose anything either. All it's doing is converting some of the energy that goes into the vortex off the first goose into lift for the next one, and so on. I understand that they do change leader from time to time, but okay, so one reason why geese will fly in formation is they're using the wingtip vortex in a positive way. The problem with looking at this induced drag from the wingtip vortices is shown on this graph. The green line shows the induced drag. From the stall, it actually reduces. The reason is quite simple. The slower the aircraft's going, the more time the vortex has to develop during the passage of the aircraft. That's a fairly simple explanation, but essentially the induced drag reduces. The parasitic drag, where the airflow is having to move aside to let the aircraft through, or you've got screen friction or interference between the different surfaces, increases, and it increases roughly as the square of the speed. If you fly twice as fast, you've got twice as much, you've got 4 times the parasitic drag, because you're affecting twice as much air in half the time. Okay, so it's having to do much more work. Of course, we don't actually measure the induced drag and the parasitic drags separately. What we're interested in is the total drag. Okay, so if you add the green and the red lines together, you get the blue one. And at the stall, it's almost all induced drag, The aircraft's flying slowly, the air's got plenty of time to move aside and let it through, but the wingtips and so on are producing much more induced drag. At some point, the two get roughly equal. It tends to be round about the minimum drag point, and that's shown on the blue curve on the point marked M. Okay. After that, the induced drag continues to fall away, but as the speed increases, the parasitic drag increases, and the total drag pretty soon becomes very close to the parasitic drag on its own. So if you take a measure to reduce the induced drag, it will improve the performance at low speed, but it may actually worsen the performance at high speed. So really you want wingtips that fall off, winglets that fall off as you go faster, but then reattach when you get slow. In fact, there was an attempt in Germany to build the FS-29, I think it was, where the wings actually extended and retracted. So you retracted them at high speed and extended them for induced drag at low speed. And it's one of the reasons on very good, strong lift days why small gliders do nearly as well as big gliders, because they're flying in the parasitic drag range, because a long wing will produce more parasitic drag. Are you happy with that? Okay. Moving on.
Peter,
Yep.
we talked about winglets on top of the wings, just as a little brief thing. Why did Boeing put winglets underneath the wing on the undersurface?
It doesn't, in principle, it doesn't make a lot of difference, because you're simply trying to stop the flow moving around the wing by having a surface that's got equal pressure on either side.
Right. Okay.
Obviously, if you put the winglets floating downwards on a glider, you're going to break them off almost every time you land.
Yeah, okay.
Right. We don't normally talk about the drag when we're looking at the performance of a glider. And it's very difficult to actually measure it. I mean, it's actually quite small, a sort of 30-to-1 glider weighing, say, 600 pounds, a typical light glider, is only producing 20 pounds of drag force. It's not a huge force, but it's obviously enough to bring the glider down. What we see instead is the change in the sink speed. Okay, and these two curves are both for K13. The red one is for the K13, showing its sink rate at different speeds if it's being flown light, i.e. with one person. The blue curve is if you've got two people, or you've ballasted it to be the same weight. And the curves are basically the same shape, but obviously the red curve has a lower minimum sink speed. That's the top of the curve, right? It's about 0.75 meters per second, whereas the normal two-up weight, it's more like 0.8. It's not a huge difference, but clearly at that speed, if you're flying at 55, 60, even 65 kilometers per hour, that's generally below 40 knots. There is an advantage in flying light. But as the speed increases from about 85 kilometers per hour upwards, that's about just over 40 knots, you're actually better off flying a K13 two-up. And that's true for most gliders. The other thing on this chart, it shows a line drawn from the origin that's a tangent to the sink speed curve. And where it touches the curve, it gives you effectively the glide angle, which for K13 in good conditions is about 27-to-1. The difference is it touches the red curve at a lower speed to the blue curve, but strangely, it doesn't change the actual glide angle. The two are the same for the light or the heavy glider. That's an important lesson. The speed you want to fly at will depend on the ballast and the effect it has on this performance curve. Happy with that? We move on. This is basically the same type of chart, but showing for a DG 1000. And the thing you notice about this is that the changeover speed is around about 100 kilometers per hour. this curve here is for the lightweight being flown. In this case, they've given the wing loading at 28 kilograms for every square meter. And the light curve, again, below 100 kilometers per hour, you're better off flying it light. As the speed increases from here onwards, you're better off flying it heavy. And when you get up to this sort of speed range, there's a very significant advantage in sink speed. Okay, look at the difference there. You're actually having to push the light glider through the air, creating far more drag. So again, this is why in competitions, most gliders will be flown as heavy as possible. The only time they've got an disadvantage from being flown heavy is if the thermals are very weak, in which case the difference between 0.5 and 0.6 meters per second might be significant. Okay, so it's only really in those weak conditions that the light glider benefits. We can use this curve to look at the effect on getting the best performance from the glider. In this case, we've got the green curve showing the glider performance. It's all nominal, so there's no units on it. And as on the K13 chart, if we draw a line from the origin to the tangent to the curve, you see it's at point B. And what that's saying is, if you fly it at that airspeed, you're getting the best possible glide angle. If you fly it slower, you might be coming down less quickly, but you're not going as far. So the glide angle is worse. But that only applies if you're flying in still air. If you're flying with a tailwind, you should move the origin to the left along the x-axis. The effect of that is quite simple. It moves the tangent point, in this case, back to position A. You're now getting the same glide angle, better, because you're actually flying downwind, but at lower speed. Rule of thumb is if you've got a 10-knot tailwind, knock 5 knots off your cruise speed. It's roughly half. It's not precisely that, but it's a good rule of thumb. You might, though, be flying into a headwind, in which case you move the origin to the right along the x-axis, and now it's gone to position C. And what that's saying is, if you've got a headwind, fly faster. We should know that. Those who've flown with me in training flights will be aware of my constant nagging as we fly through lift and sink. Speed up, we're in sync, slow down. And that's shown by shifting the origin up or down. If you're in sinking air, you raise the origin to whatever sink rate you're getting. And now the tangent is giving you a position well long. And of course, you could be in that very unhealthy position, flying through sink on a headwind, in which case the origin would be somewhere up here, and the tangent would be somewhere in this area. In other words, you need to increase the speed, partly because you're flying into wind, and perhaps even more because you're flying in sync. And the simple answer is, and it works out on, say, approaches on strong wind days, rather like today's flying, where you will have a headwind, you're landing into wind, and you may be flying through sink. And the answer is fly as fast as you possibly can. Because that way you're going to get the best performance. Any questions about that? Right. Now, I don't know about everybody here today, but I don't carry this chart around in the glider. Right? And I don't start drawing tangents. There are much more interesting things to do when you're actually flying. So a man called Macready came up with this simple device. It's the ring around a variometer. So ring around a variometer, you'll see that. And it rotates. So it's not necessarily set as it is. In this case, the arrow there is set to 0. Now, when you're flying through sinking air, it is telling you if you're coming through air that's 1 meter per second down, or roughly 2 knots, you should be flying at around about 105 kilometers per hour. if you hit stronger sink, you should then increase the speed to 125, something like that. 3 meters per second down, speed over 140 kph. It's a simple way of that. Each of these rings is calibrated separately for each glider. So in this case, it's saying it's an ASW28. Right. So if you do have a ring, make sure it's for the right glider. I once flew a K18 that had a twin austere ring. It made no sense whatsoever because twin austere always would be flown faster. But the reason the ring rotates is that you can rotate this ring to the average climb rate you're getting in thermals. And the average climb rate is typically about half what the Vario says at best. So if you're getting 4-knot thermals or 2 meters per second roughly, the average climb rate you're probably achieving is about half that. But by rotating the ring to point at the average climb rate, it then adjusts the speed to fly. And so you simply fly faster than you would if you're in still air. Okay, because you're not in still air, you're spending more time in thermals. I have to say though, the Macready ring is beginning to fade from the scene. The reason is a lot of the modern variometer systems do this in the background. They do it electronically and they'll produce the speed to fly at any one point. And they'll even tell you what the average climb rate is. The average climb rate you're rotating to, though, is not actually the one you're achieving. It's the one you expect to achieve in the next thermal. And we'll see why in the next bit. We've got 3 glider pilots here. They're all at 5,000 feet in the same bit of sky. They've climbed up together. Okay. Now, pilot A is a very intelligent person who's listened to this talk. And he believes his Macready ring, which tells him to fly at whatever speed. And so he flies at that speed and he sets off. Obviously, it's a little bit exaggerated thing. He gets to the thermal and he starts climbing. So round and round he goes until he gets to here. Pilot B is your average club pilot who sort of have heard about this speed to fly thing, but actually likes staying high. He doesn't like flying faster than, say, the best glide speed, or even as fast as that. So he sets off more slowly. He glides along, he's sinking down, but he's still higher when he gets to the thermal. The problem is he's taken longer to get there. So as he turns and keeps turning, getting up to the top of the thermal, he gets to position B and looks up and sees that pilot A has actually got to cloud base ahead of him. Right? Because the Macready ring is accurately converting the performance of the glider to get to this point sooner. Pilot C is our junior whiz kid who knows if he flies faster than other gliders, he will overtake them. So he sets off and he's flying much faster, so his sink rate's much higher. And sometimes he gets to the bottom of the next thermal, and sometimes he doesn't. If he does, he starts thermaling, thinking, well, I've got there first. He has. But by the time he gets up there, he finds, if anything, he's still behind pilot B, who's flying more safely or securely. And pilot A is well above him. Okay, so you could argue, well, if all you do is trying to stay up, pilot B may have the best strategy, but it certainly makes a big difference if you start going cross country as to how far you get. And you may say, well, does it matter if I take longer getting round? Well, it does if you're ending up at 6 o'clock in the evening, 50 kilometers from home, and wondering where the next thermal's coming from. So speed is also relates to distance. If you want more on this, probably the best book is Helmut Reichmann, Soaring Across Country. It's got an awful lot on this. I think this diagram may even come from the book. All happy with that? Good. Right, moving on. If you look at the end of the tip, this is moving back to the aerodynamics of the wing, you'll see that the tip is at a lower angle than the root. The reason is simple. If it's at a lower angle of incidence, When the main part of the wing reaches the stall point, the tip will still be producing lift. That's a good thing, because if the inboard part of the wing stalls, but the tips are still working, you've still got some lateral control and it's not likely to drop the wing. Some gliders have very little washout, as it's called, in which case they are quite likely to drop a wing at a stall. The other reason is that the narrower the tip is, the narrower the chord of the tip, that's the distance from the front to the back, the more likely it is to stall early. So aircraft with very narrow tips, like for instance the Ventus series, are likely to drop the wing unless there's some washout. Some other gliders, particularly the Slingsby Swallow and the Capstan, have got excessive washout. They've got about 3 or 4 degrees. And that's because the ACC, who were looking to buy them, insisted that they weren't able to spin. So whatever if you ever try to spin a Capstan, you know every time you bang in the rudder, it sighs a little bit and then carries on flying straight. Okay, same with the Swallow. Other modern ones, like the, well, relatively modern, like the IS series from Yugoslavia, have very little washout. And I tried stalling an IS-30 and every time it dropped a wing. Not the right kind of glider to fly in slowly. Okay, so that's just a quick diversion into why the tips varied. It does have some benefit in terms of induced drag, because obviously if the tip is producing very little lift, then there's very little induced drag coming from it. And so having a lot of washout can reduce the induced drag. And that's probably the reason why Capstans actually climb quite well, although the glide performance is spoilt by the excess washout. Another bit of aerodynamics which does crop up in some of the bronze questions and sort of related to the previous one is all the observant ones will have noticed that the aileron that's moving up moves much further, normally about twice as far as the aileron that's moving down. If you think about the drag, obviously adverse yaw caused by increasing the lift can be a problem in getting any glider to turn. On some of the early large span gliders, it was almost more powerful than the rudder. A simple arrangement of the bell cranks in the wings ensures that as you move the stick, the upgoing aileron moves far more, creating a little bit more drag. The aileron going down produces less drag and less lift, but it still doesn't affect the roll rate that badly. Okay, so then that's just because in some of the bronze papers that crops up. Right, am I going too fast or everyone happy? Okay, so it's all really revision of common things. In a turn, well, first of all, the wing has to produce sufficient lift to support the weight of the glider. In a turn, the lift is inclined to remain roughly perpendicular to the wings, but it still has to support the weight. Therefore, the vertical component needs to remain the same, which means that the overall lift has to increase. We're all aware of that. And the effect is, as you go into a turn, if you don't do anything about it, the nose will go down. The glider will try and compensate by increasing the speed and therefore the lift. Okay. The amount varies. If you've got a relatively steep turn, then in this case, about 45 degrees, the vertical components of the lift is still balancing the weight, but the horizontal component of the lift is about the same. Okay, so you've increased the lift by a factor of 1.4 or root 2. Okay, and that shows up particularly in the effect on speeds. So we've got here gliders flying level. The G rating is 1 because it's just level, it's just the mass of the glider, more or less is the same as the weight. Stalling speed of this glider is 33. 20-degree bank, the G loading is 1.06, and the stall speed has only increased by 1 knot, barely noticeable. 40 degrees, now the G loading is 1.3, you're beginning to feel it. and the stall speed goes to 38. 60-degree bank, in fact, the force into the turn is twice that of the lift part, but the G load goes to 2 and the speed now goes to 46 knots and it becomes significant. All right, but remember, this is if you're actually pulling a balanced turn. If you relax the back pressure, the G drops back down to 1 and the glider really immediately carries on flying normally. If you're still banked like that, it's going to drop its nose quite a lot, but recovery from a stall in a steep turn is simply backing off. Moving on a bit. You've not seen this chart before? Again, we don't carry it in the glider, but it's the knowledge of what it is quite important. I think this is probably for K21, looking at speeds. Okay. Essentially, it's the area in which you can load the glider without breaking it. Okay. If we look at the curve going upwards, where it says not possible, now let's look at what that means. 1G, level flight, you can do that at 40 knots. Okay. You can't fly this glider pulling level flight at 20 knots. It will not do it. Therefore, this becomes impossible. You can pull 2G on this glider if you're flying at roughly 60 knots. You can pull 4G if you're flying at 80 knots, but you can't pull 4G at 60. So all of this, the glider simply won't do it. Okay. The lower part of the chart is all about inverted flight. Okay, and the reason why it's smaller is the spars and so on are designed, and the wing section, to for normal erect flight. This line is the VNE. Okay, if you exceed that, there's on the type of glider, but certainly in a fiberglass glider, you're likely to cause some distortion of the airframe to the point where it may well be damaged. And here, if you're pulling more G, then again, you're in a damage area. The reason it drops off is you can pull 5G at 90 knots or thereabouts. If you try pulling 5G at 140 knots, you've got the double load on the airframe. You've got a higher airspeed and you're pulling excess things. So that area is a definite no-go area. This you have to stop entering yourself. You could go past these lines. This part you can't go past. The glider won't accept it. And the whole thing is referred to as a flight envelope, which is not a brown envelope in which your certificate arrives. Okay. That all implies that we're not taking, that this is all in still air. If there are gusts around, a strong gust is defined as roughly 2,000 foot per minute sharp edge gust. It starts lobbing off this bit, because if you're in this area, you're pulling 5G at 80 knots or whatever, then you're going to overstress simply because of the sudden load of this vertical gust on the aircraft. And this is generally referred to as the rough air maximum speed. Okay. Speed at which, if you exceed it, you can overstress the glider. If you're flying in rough air, and rough air in this case would be pretty rough. There's another one. As the speed increases, even a small gust will lob off the end of the move. Interestingly, on this one, I can't see it because I've got stuff in the way. Oops, go back again. There are two maximum speeds. One is the demonstrated maximum, which is usually a little bit higher than VNE, but that's strictly test pilot area, particularly in glass fiber gliders, because they do suffer from aerodynamic twisting loads as speed increases. For one thing, the washout at high speed starts to produce negative lift and the tips start to bend downwards. That twist can have quite an effect on the wing. There is another speed, VA, and usually it's pretty close to VB. VA is the maximum speed that you can use any one control, full movement of the control. And say on nearly all gliders I've seen, the VA and VB, for good reasons, are pretty close together. So we don't normally worry about that. But if you see on the glider maximum rough airspeed, then you can be pretty certain that the maximum control deflection of any one control is about the same speed. A little bit about central pressure and wing. A wing, we all need tailplanes on conventional gliders. And the reason is quite simple. A normal airfoil, which is maximizing lift rather than stability, as the angle of attack increases, the center of pressure moves forward. Now, center of pressure is simply defined at the point at which all the sum of forces across the whole wing appear to act. Okay, so as you increase the angle of attack, the center of pressure moves forward. The front of the lift is producing more lift proportionately than the back. Similarly, if you decrease the angle of attack, the center of pressure moves backwards. Now, if you stop and think about that, if you're flying along in a wing and no tailplane, just a plain ordinary wing, and it momentarily increases its angle of attack and the center of pressure moves forward, that will tend to increase the angle of attack even more. The situation is unstable. If you ever take a model aircraft wing off the model aeroplane and try flying it, you'll see it rotating very rapidly backwards down to the ground. For that reason, that as soon as the angle of attack increases, the pressure moves forward and round it goes. Okay, how do we stop that? Well, we'll come on to that a bit. But so you see that the wing basically is unstable. Right? In normal airflow, the center of pressure and the weight are acting fairly close together. But if you increase the angle of attack, the total reaction on the wing is ahead of that, and it is a pitch-up moment. Okay, until you reach a stall, and then it changes a bit. Okay, so what restores the angle of attack is simply the tailplane. As the angle of attack increases on the wing, it also increases on the tail. But the tail is much further away from the center of gravity than the wing, and therefore that provides the restoring moment. As long as the tailplane is at a lower angle of attack than the wing, and that's simply a bit set. The incident is usually about 1 or 2 degrees. So wings on their own, conventional wings, are unstable. They need a tailplane. There was a French series of gliders that had no tail, and not the other way of doing it is a swept wing, but they didn't have a tail. You can make a wing where the center of pressure doesn't move, or in fact it even moves backwards, but that involves having a big reflex curve at the back end. And those wings are not very efficient. So that's why tailless gliders, as Mike Bird once said, there's nothing wrong with a tailless glider that adding a tail won't cure. Okay. So let's look at a conventional glider in slow flight. You can see that center of pressures move forward. Okay, that's being countered by the forces on the tailplane. The tailplane's having to do some lifting. To make the tailplane lift, it's actually got the elevator up in order to hold that attitude. So we've got significant forces on the tail countering the difference in these two bits. So slow flight, it's not very efficient. The other thing that's not very good is the glider itself, the fuselage, is presented at less than the optimum angle to the airflow. So now this glider is producing more drag, partly from the tailplane and partly because the airflow is bad. Okay. In conventional cruising flight, the tailplane is now producing much less force. The elevator is probably pretty well neutral. Okay, this is an unflapped glider, I must emphasize that. So now it's pretty efficient. The fuselage is in line with the airflow and the load on the tailplane isn't great. If we go on and increase the speed, right, the angle of attack is reduced, but that's because the elevator is now pointing downwards, producing a small lift, and the tailplane is having to produce a large downforce. And again, the fuselage isn't lined up with the airflow very accurately. Therefore, it's producing more form drag. Okay, this is an unflapped glider. It's mostly, if the glider is well designed, its best lift over drag speed will mean the fuselage is in line with the airflow and there isn't a lot of force either way on the tailplane. But if you fly faster or slower, the glider will be less efficient. Some gliders weren't very good at that. Some of the earlier ones, that, for instance, the Dart has a very strong nose down appearance in normal cruising flight. If we look at the same situation on a flat glider, it's quite different. Normal flight, flaps in line, you can just about see that. Glider is in line with the airflow, not much load on the aircraft. And if we go on in flight, there is a slight downforce here caused by the flap having to be up, but the loads still are fairly light on the tailplane. And this is where flat gliders at the normal lift over drag, best lift over drag speed, are reasonably efficient. Unflat gliders are, sorry, but at speeds above and below that, the flat glider will win out. And you can see this, you know, they work better in thermals, and certainly as the speeds increase, the flat glider has the advantages. The disadvantage, of course, being it's more complicated. All happy about that? Good. And so we've mentioned a bit about centre of gravity. As we know, it's a two-seater, so pilot 1 has a big influence on the centre of gravity, pilot 2 less so because he's much nearer the range. We can put ballast weights in the front, we can even ballast the tail on things like DGs and so on, two-seaters. Okay, but for every glider, there's a forward and aft limit to this. The further forward the limit is, the more the tailplane's got to do to keep the nose up. And then expressing it very crudely here, but the load on the tailplane will increase. The further aft the centre of gravity is, the less will be the load on the tailplane, but the less stable the aircraft will be. So it's a touch. And normally the aft limit is set at the point where recovery from a spin is perfectly normal and straightforward, i.e. after 3 turns spin, it will recover within 1 turn, which is the JAR standard. That's the joint airworthiness requirement. If it's outside the range aft, then you might have a problem in a stall or spin about the recovery. If it's forward of that limit, the tailplane's really having to do a lot of work, and you may find that you run out of elevator at the round out, quite apart from any other issues. The one reason why moving the centre of gravity aft has an adverse effect on stability is simply that the distance gets less. With the centre of gravity aft, you've got less distance between the tailplane and C of G. And remember, it's the C of G where all these actions are taking place. Okay, so again, the further aft it moves, that's it. And stability is apparently straightforward for gliders, but there's more variation than you imagine. Nearly all gliders are statically stable. That is, if you trim them out 50 knots and let go, they'll carry on flying at 50 knots. Okay. It'd be quite surprising to find there were some, the very early LS1s were not even statically stable. In other words, you might trim it out at 50, but pretty soon it would start increasing or decreasing. Now, a stable aircraft, imagine you're flying along at 60 knots and you pull the nose up, so you're doing 40 and let go. It's trimmed at 50. Sorry, yeah, 50. The nose goes down. You actually pass through the previous limit, the speed increases, and because you're now flying above the trim speed, the nose rises and increases and so on. But each time it's less. And eventually it will settle down back to the trim speed. That's a stable, dynamically stable aircraft. And if you want to try it for yourself, best to, if you haven't done it before, do it with someone who's done it in a two-seater. And in fact, if you try that in a twin, you'll find the twin is reasonably stable. Rarely you might have a glider where you decrease the speed, let go, and it increases and then decreases, but never stops doing that. It will carry on forever. There's a few gliders where that's close. Some gliders, though, if you slow it down a bit and then let go, it will increase and fly faster, then it will decrease, but it will decrease more each time and then increase more each time. I'm sure some of you know this, that one of our regular training gliders shows this. And that's K13. If you're flying a K13, trim it to 40, push the nose down to 50 and let go. And I guarantee you'll be grabbing the stick within 2 or 3 cycles. And one of the reasons is to do with the way the trim works and also to do with the volume of the tailplane. That's the area of the tailplane times the distance from the center of gravity. So quite a few gliders that people like flying are actually unstable dynamically. They're easy to control in pitch. It's very easy to change speed. But if you're in cloud in an unstable glider, it becomes very difficult. You can't just rely on leaving it alone to sort itself out. Whereas a stable glider, you can. Remember, a stable glider is stable as long as the center of gravity is forward of the minimum position, the minimum rear position. And some gliders, they're about neutral if it's in the middle, but become unstable if the center of gravity goes towards the back. It's one reason why when we send people solo, we like them to be flying at least a few pounds, maybe 10, 20 pounds above the minimum weight, so that the center of gravity is forward and the glider is more stable. Moving on, lateral stability comes from dihedral. How does that happen? If the glider momentarily banks, it will start to slip towards the lower wing. The lower wing is presenting itself at a higher angle of attack, and that will produce more lift, and it will correct. Okay, most gliders are like that. Quite a few modern glass gliders on the ground have very little dihedral because in flight, the wings bend upwards. Okay, so some of the longer span glass gliders like that, others aren't. There's another interesting thing here. Dihedral works like this, but so does wing sweep. If the wings are swept backwards slightly, it has exactly the same effect. The airflow on the swept wing becomes a higher angle of attack if the wing goes down. Conversely, if the wing is swept forwards, it has an adverse effect on roll stability, because the wing that has gone down is presenting itself at a less of an angle to the airflow, so you get less lift. And can we think of an aircraft that we all know and love that's got sweep forward? K13 again. K13 was developed from the K7. The problem with the K7, for those who've flown it, is you can't see out from the back seat because the wing's on either side of your head pretty well. So when they decided to make it mid-wing so the instructor could see out, they lowered the wing, but they couldn't lower it where it was because the spar would go straight through the person in the back seat. So they had to move the spar junction back behind the rear seat. To keep the center of gravity in the right place, they then had to sweep the tips forward. They then found, obviously, that it was less stable in roll, and to counter that, it needs more actual dihedral. So if you look at a K7 wing, it almost looks the same as a K13, but without the sweep and with less dihedral. So they were countering the loss of roll stability with the sweep forward by sweeping it, by giving it more dihedral. Sideways airflow. Related to that is spiral instability. Most gliders have spiral instability. If you start a gentle turn and either keep the stick in the middle or even let go, there will be a tendency for the bank to increase. Reason is very simple. The wing on the inside is going less quickly and it will start to go down. The wing on the outside is going faster, it will tend to pick up lift. In fact, in normal balanced turn, where you're controlling it, you'll end up with the stick slightly to the outside of the turn. Okay, that's normal. So here we're talking about if you're not actually controlling it. So there's a tendency for, as on the left, for the inside wing to start going down and the glider's nose goes down. And if you don't do anything about it, you'll end up in spiral dive. Again, it's a feature of flying in clouds. You can't just rely on the stability of the aircraft once you start turning. It's also made worse if the fin area is large, because as the wing goes down, there's more fin area, which tends to be pushed to the outside of the turn. And so the glider is more likely to go into a turn. It's a big issue with model aircraft, free flight model aircraft, that if you've got too much fin area, it will tend to go into a spiral dive. If you've got more dihedral, that will tend to reduce the tendency for the spiral dive, because the downgoing wing will actually have a higher angle of attack and it will tend to self-restore. And if you also have a small fin area, that will stop the yaw developing. Obviously, you need a fin to provide yaw stability, but the fin area makes a big difference on how it behaves when it starts to turn. The Lebel has got a very small fin area and has very little tendency to go into a spiral. Right. But if you fly the 419, which has got a huge fin area, you find that spiral stability, instability does exist, especially with the long span. So just by looking at a glider, you can have a reasonable guess as to whether it's got spiral instability. A lack of dihedral and a large fin area will definitely give you spiral instability. A little bit of dihedral or more dihedral and a small fin area may be less stable in yaw, but less likely to go into spiral dive. Again, it's the kind of thing that's useful if you're flying in cloud, where you can't see the divergence from straight flight, except on the instruments, of course. Right, moving on, not far to go. Seen from the front, the lift spread across the top of the wing is roughly in a sort of elliptical path. Okay, most of the lift is coming from inboard and it reduces the top. It's one reason why the Spitfire had a very efficient wing, that the area of the wing was exactly matched to the distribution of lift. So each part of the wing was doing the same amount of work. In normal flight, the lift from the wing is supporting the weight of the wings themselves and the weight of the glider. Okay, so there's a tendency for the wings to bend upwards. That's partly relieved by the fact that the wings have weight themselves. And of course, the weight of the wing isn't causing any bending moment on the wings. If we go into a turn, we're producing effectively higher weights. The mass stays the same, but because we're turning or pulling out of a dive, you know, the bottom of a loop, the aircraft reaches 2G, say, so that's doubled. The wing weight has also doubled and the lift has doubled. Okay, so the same sort of pattern that emerges. Okay, all happy with that? Good. Well, there is a situation though where the wing weight doesn't increase, but the load does. And that's the winch launch. So we've got the weight of the glider, which is at 1G. It's not turning or maneuvering, it's just going up the wire. And the wings are still at 1G, but you've now added a pull underneath. And typically, you know, if you've got a 1,000-pound glider, you can easily have 1,000 pounds pull on the cable. That load is not relieved by the increase in the wing weight because it hasn't increased, but the lift has still got to be doubled. And that's one reason why the winch launch speed is significantly lower than, say, the aerotow speed, because you've got an unrelieved additional load on the center of the aircraft. And I know some of you have launched ASW 20s and 19s and looked out at the wings on the winch launch and immediately looked back, because it's frightening. You can actually see this extra bending moment as the wings appear to bend a long way. Basically, there was one of the last gliders that had pure glass spars. And glass fibre does bend quite a lot compared to, say, the carbon spars of later years. But that's one reason why the winch launch speed is significantly lower. In some cases, the Germans just tended to calculate, would the wing be strong enough, rather than working out what load it would actually take. So, for instance, the German rating for K-13 is about 55 knots, 56 knots. But when it was recalculated in the UK, they found that the wing was actually strong enough to go to 63 knots. This is all based, again, on hitting a strong gust, because if you're already putting a big bending load on the wings, then you hit the gust, that increases the cable load immediately and increases the bending moment. Happy? Good. I think this is the last bit. Okay, another thing that affects the span-wise loading you need to be aware of. In plane flight, normal flight, again, the majority of lift is coming from the inboard part of the wings. The minute you open the brakes, you're destroying the lift on a significant part of the wing. Okay, the middle bit's still doing its job, but proportionately, the lift outboard increases. And again, you can see that if you watch a fiberglass glider on approach, you can tell when they open the brakes, not simply because you see the brakes opening, but you can see the wings bending quite significantly. If you've got one of the older flapped gliders, then you've got the situation where the flaps weren't connected with the ailerons. You have the flaps down, which is sort of increasing the load in the middle. But remember, that's changing the attitude or the angle of attack of the inboard part of the wing. You're effectively lowering the nose. But that means the outboard part is now producing negative lift. And it's quite amusing to watch one of these older flat gliders on the approach, that you do see the tips bending down at the same time as the main part bending up. Okay. They've got around that essentially by interconnecting the flaps and the ailerons, so effectively the whole of the wing becomes flapped. Are you all happy with that? Good, because that's it. You now know probably more than I know, because I've forgotten most of it. Any questions? No. Can we all go and get our beer then?
I think one thing. Okay, one thing that might be worth mentioning, because I think people do find it confusing, is the angle of attack in relation to the airflow, as opposed to what angle you are with the ground. I know that sounds silly, but
no, you're right.
Yeah,
I mean, the angle of attack is simply the angle which the air hits the wing, whereas the angle of the wing to the ground or fuselage is more to do with the angle of incidence, which is Gill. And this does vary, obviously, on all gliders. A good example to look at is the Vega, where the angle of incidence on the wing was very small, but that meant the angle of attack on the ground would have been very low, and it would have needed a high takeoff speed and also a high landing speed. They got round that by giving it a tall undercarriage, right, which supposedly helped it at the high-speed cruise end, because the fuselage is then in line with the airflow, but made it a pig on the ground run. Okay, so another example, if you look at LS4s, for instance, very nice gliders, and quite a few of the LS series, they're not good gliders if you do fully held off landings, because the undercarriage is relatively short. The incidence is set to give you a reasonable angle of attack for that. But if you try doing a fully held off landing, you probably finish up touching the tail wheel first. and at which point the main wheel would then descend fairly firmly onto the ground. The ASC Spirit that flew the American thing, you would have broken the glider if you did a fully held off landing. The main wheel would have been about 2 to 3 feet above the ground when it stalled. So yes, angle of incidence is not the same as the angle of attack, but you can tell actually by just looking at a glider from the side. You can get pretty good if you're flying a new type. You can get a pretty good idea what that's going to be like.
Thanks.
Any more questions or suggestions?
Yeah, one for me.
Yeah.
Could you go through all that again, but flying it, how it all works when you're flying inverted?
What, the loading?
How it all works when you actually invert.
There's always one.
You've got to get it back.
Right. Well, you won't find many questions on the bronze paper about inverted flight. But the simple thing is, in principle,
Angle of attack.
Oh, the angle of attack. Well, the first thing is the airfoil has got a positive, for normal gliders, not about the pure aerobatic gliders, has got a shape that produces lift efficiently when they're the right way up. If you've tried flying, I've only flown inverted in things like K-21s and not for long. Apart from feeling horrible, the sink rate is phenomenal. Because you're trying to, if you make that curved airfoil, now trying to produce lift from what would be the undersurface is now become the top surface, and the air's trying to flow around and produce lift. So you've got to get it to a higher angle of attack to get any lift. And it's horribly inefficient. It is strangely slightly more stable in pitch when it's flying inverted, because effectively the reflex part of the wing is now helping the centre of pressure movement. So it's slightly more stable, but of no earthly use to anyone who is sane. And if you're not sane, you shouldn't be here. There are people who like aerobatics in gliders. They like spending 50, 60 quid on a tow to 4,000 feet and beating the tug back to the airfield. Am I expressing a view here about my thought of aerodynamics? Aerobatics in gliders, but certainly for those that proper aerobatic gliders like the Swift, the wing section is almost entirely symmetrical. Right, so they have a higher stall speed because they're not that efficient at producing the lift, but the wing then work reasonably well inverted, but they're just not practical.
Okay.
Sorry. Okay, yeah. And in terms of the loading, you can still load them less. The pure aerobatic aircraft have symmetrical spars, so they're just as strong bending the wrong way. But again, that increases the overall weight of the glider. So they're not efficient.
I knew you'd know the answer. Thank you.
Yeah, avoid that. Right, anything else? Okay, I don't know if some of you will have learned nothing from that. I hope some of you learned nothing, otherwise you shouldn't be sitting in the back seat.
No, but it's always good as a reminder. Yeah, for sure. That's brilliant. Thanks, Pete.
Put that together simply by looking at some of the past papers and trying to find diagrams for each of the questions on the past papers. So if you do sit the bronze principles of flight, you should have covered enough to get past. Not saying we covered everything, but it's not that difficult. It's a section most people pass.
Yeah,
that's really good, Pete. Thanks. I need to go and blow some bubbles, man.
So yeah, okay. All good.
Thanks a lot.
Brilliant, Pete. Thank you very much.
See you soon.
Thank you.
Thank you all.
Cheers.
Cheers all.
Bye-bye.